Okay, good morning, everybody.
Good morning.
Let's get started. Okay, so what we're going to be doing today, we're going to be starting a new topic, and it is one of the most important topics in digital signal processing, and that is the discrete Fourier transform, and in general, it is the frequency analysis.
The screen's not on.
Thank you.
Are you going to record or Zoom?
I did.
Okay, Mr.
Frequency analysis, and in particular, the discrete Fourier transform. Every time you look at the spectrum of a signal, whether you're looking at it in the spectrum analyzer, whether you're looking at it on a screen, whether you're looking at it in a paper, most likely that spectrum was generated using the discrete Fourier transform. So what we're going to be doing today is we're going to introduce the discrete Fourier transform. We're going to relate it to other transforms. We're going to try to understand, when we look at the discrete Fourier transform, how it would relate to the other transforms. Make sense? Okay. So again, Fourier analysis is one of the most important topics in digital signal processing, and it enables us to find the spectral content of a given signal.
Spectral or spectral?
Spectral. Spectrum. Spectral. Okay. Now there are some transforms that we might be familiar with that we have seen previously. And we're going to briefly review these transforms before we introduce the discrete Fourier transform. So depending on the signal that we are trying to look at the spectrum for, whether it is a continuous or a discrete time signal, and whether it is periodic in time or aperiodic, there are tools that are available that enables us to look at the spectrum of the signal. So if the signal is periodic and it is continuous in the time domain, what is the tool that we use to look at the spectrum of the signal? We use Fourier series. If the signal is continuous and the signal is aperiodic, what is the tool that we use to get the spectrum? Fourier transform. If the signal is periodic, but it is in the discrete time domain, we use the discrete Fourier series. And if the signal is aperiodic and discrete, what is the tool that we have already seen?
Discrete time Fourier.
Excellent. Discrete time Fourier transform. So this is Fourier series. This is Fourier transform. Discrete Fourier series and discrete time Fourier transform. Now we're going to review all these and we're going to look at them and see what, refresh on what each one means. But what is our objective in what we're doing in this part of the course? We're going to be introducing a new tool that we're going to call discrete Fourier transform. Good. So we're going to be introducing a new transform, that is the discrete Fourier transform. And our objective is first introducing that transform and understanding how we do the calculations with that transform. But more importantly, to relate this transform to all these other transforms. Make sense? So we're going to see how this relates to all these other transforms. So if you want to calculate Fourier transform, what is it we're going to do? We're going to calculate the discrete Fourier transform. Good? If you want to calculate the Fourier series, what are you going to do? You're going to calculate the discrete Fourier transform. If you're going to calculate the discrete time Fourier transform, what is it you're going to calculate? The discrete Fourier transform. Why is it we like the discrete Fourier transform? As we will see, because we can use the computer to calculate it. And then if I can use the computer to calculate it, and then I can relate it to any of these transforms, then I can just use it to calculate any of these transforms. Make sense? Okay. So let's do a quick review of different transforms that we've seen. And starting with the continuous time Fourier series. As we said, we use the continuous time Fourier series for a signal that is periodic and that is continuous. So if I have a signal that looks something like this, and I want to look at the spectrum of this signal, this is time domain, then we use the Fourier series to calculate the spectrum of the signal. How does the Fourier series of the signal would look like? Anybody remember? We're gonna get. Go ahead. It's gonna be discrete, and it's gonna look something like this. And these are the harmonics that make up this signal. So, if I have a signal that is periodic, x of t equal x tilde of t plus t, periodic, then x tilde can be written as the summation from k equal negative infinity to infinity, ck e to j k omega 0 multiplied by t. So this represents ck's. And ck's are given by 1 over t, the integration over one period, x tilde of t e to negative j k omega 0 t dt. And these are, we call these harmonics. So when k is 1, is omega 0, the first harmonic. When k is 2, second harmonic. K is 3, third harmonic, and so on and so forth. And omega 0 is equal to 2 pi divided by t, where t is the period of the signal. So from here to here is t. Okay. So if I want to use, if I look at this for a series, we notice that the time domain, the signal is continuous and it is periodic. And if you look at the frequency domain, the signal is discrete. So this represents the time domain, and this is the frequency domain. When we do the Fourier series, what the Fourier series says is that you can write this signal in terms of these frequencies: C0, omega 0, C1, omega 1, C2, omega 2, and so on. Does that make sense, everybody? Okay. Can we use a computer to calculate this transform? No. Why? Because we have continuous, because we have summation to infinity, and therefore we're not going to be able to use a computer. We have the integration, we have the infinite summation, and we have the continuous variable t. Okay. The second transform that we will encounter is the continuous time Fourier transform. Fourier transform. And as we said before, the Fourier transform, we use it when the signal is continuous in the time domain and it is aperiodic. So this is one of the most used transformation. So if I have a signal x of t, where the signal is equal to the integration from negative infinity to infinity, x of w e to j w t dw. This is how I get the signal in the time domain from the spectrum x of w. And we can calculate x of w, and it's going to equal the integration from negative infinity to infinity, x of t e to negative j omega t dt. What is an example of using the Fourier transform to calculate the spectrum that we're familiar with? The sink. If I have a rectangular pulse in the time domain, in the frequency domain, the spectrum is going to look like a sink. Okay. Another example. If I have a sinusoidal signal in the time domain, what is the spectrum of the sinusoidal signal? In the frequency domain?
Two spikes.
Yes, excellent. Two impulses at omega 0, negative omega 0, and magnitude of a pi. And this is if we have a cosine omega 0 multiplied by t. Okay. Again, if you look at the Fourier transform in the time domain, it is continuous And in the frequency domain, it is also continuous. This is x of t, this is x of w. And again, we cannot use the computer to calculate. Because we have t, w, and the integration. The continuous variables and the integration. And the integration also from infinity to negative infinity to infinity. Okay. Now somebody might be confused. Anybody confused on something we just did that contradicted what we just said? Is it?
How is the Fourier transform of that cosine continuous?
Excellent, yes. I mean, that's a good question. And we said this signal is aperiodic, and we put a periodic signal here, isn't it? Like, seems to contradict what we're saying. Make sense? But this is a special signal. So just consider this an exception, the cosine and the sine, an exception that we use the Fourier transform for. In general, we're going to look at the signal that is finite in the time domain. It's going to give me a spectrum like this, a continuous environment. This is the special case that we added it. Very good, Quinn. Again, just accept it as a special case. Okay. The next transform is a transform that you might have never heard of. And that is the discrete Fourier series. And actually, I'm just going to go back and just write a few lines here. So you're not really very bothered by this. But if I have a cosine omega 0 t, this is equal to 1 over 2 e to j omega 0 t plus e to negative j omega 0 multiplied by t. And if I have x of, I can calculate x of t, that is equal to 1 over 2 pi, the integration of a pi multiplied by delta of omega minus omega 0 e to j omega t, the omega, and this is going to equal to pi over 2 pi e to j omega 0 multiplied by t. Okay, so what is it I've done? I made this special case even more confusing. All what I'm saying is this. If you give me this signal, if you give me, I look at the spectrum and I saw a spike of a pi here and a pi here. What is the signal that gave me this signal? I'll tell you it's easy. Just look at the inverse Fourier transform, which is we just wrote here. It's going to equal 1 over 2 pi, the integration of that signal that you observe, e to j omega t. Since this is a delta, I'm going to take only one of them, a delta of omega minus omega 0, I'll plug it here in the formula for the Fourier transform from negative infinity to infinity. That is going to equal to pi over 2 pi. And what is the integration of a delta omega minus omega 0 e to j omega t? Is going to equal e to j omega 0 multiplied by t. Remember this from the shifting property of the delta function? So what this tells me, what this says, is the following. If I have e to j omega 0 multiplied by t, then in the frequency domain is going to equal to a pi multiplied by delta of omega minus omega 0. Good? But then I can say, oh, but the cosine is made up of 1/2 e to j omega 0 t plus e to negative j omega 0 t. And therefore, this is going to equal to a pi of delta of omega plus omega 0 minus omega 0 plus a pi multiplied by delta of omega plus omega 0. Does that make sense? So that's how we find the Fourier transform for a cosine. We can do the same thing for a sine. And again, it's a little tricky, and it is, again, a special, you can think of it as a special case. Okay. This is 1/2, sorry. 1/2 e to j, which is this one. Okay, so continuing, the next transform is the discrete time Fourier transform, and this applies to a signal that is discrete in the time domain. So x delta of n plus n, this is periodic, and x tilde of n, tilde means it's periodic, so if you're just wondering. 1 over n, the summation from k equals 0 to n minus 1, capital X of k, e to j 2 pi k multiplied by n divided by n. Bless you. And x tilde capital of k is going to equal the summation from n equals 0 to n minus 1, small x tilde of n, e to negative j 2 pi k multiplied by n divided by n. And here too, x, the capital X tilde of k is going to be periodic with a period that is equal to n. Okay. So if you look at this transform, in the time domain it is discrete, in the frequency domain it is discrete. Discrete and periodic. In the frequency domain, it is discrete and periodic. And since we have a summation and it is finite length, we can use the computer to calculate. Okay. Finally, the last transform we're going to review is the discrete time Fourier transform. And the discrete time Fourier transform, if you remember, is given by x of n equal 1 over 2 pi, the integration of negative pi to a pi, x of e to j omega n d omega, and x of e to j omega is given by the summation from n equal negative infinity to infinity, x of n e to negative j omega multiplied by n. So for this transform, the time domain, the signal is discrete. And in the frequency domain, the signal is continuous. And it is also periodic. And again, we cannot use the computer to calculate because of omega. Okay. Everybody remembers the discrete time Fourier transform? We calculated, we can take x of z, replace z with e to j omega, which is the same as calculating it over the unit circle. Okay. So given all these four transforms, what we are going to do now is we're going to introduce a new transform that enables us that we will be able to calculate using a computer, and that will be related to all these transforms. And that new transform is called the discrete Fourier transform. Okay. So the next transform is the discrete Fourier transform and the inverse discrete Fourier transform. So what does this discrete Fourier transform say? It says given a finite length sequence x of n. So give me x of 0, x of 1, all the way to x of L minus 1. Then we define the n point DFT for n greater than or equal to L. as the following. X of k is equal the summation from n equals 0 to n minus 1 x of n e to negative j 2 pi k multiplied by n divided by n, and this is for k between 0 and n minus 1. And we have the endpoint inverse dft, and that is going to be x of n equal to 1 over n, the summation from k equals 0 to n minus 1, capital X of k e to j 2 pi kn divided by n, and this is for n between 0 and n minus 1. Sounds good? So this is the new transformation that we are introducing that we have not seen before. Now both, as we can see here, both x of n, which is in the time domain, and x of k are finite length, and therefore we can use the computer to calculate and of course, like when we say we can use a computer to calculate, what do we mean? I mean, you can have MATLAB symbolic toolbox calculate this transform, but what is it we mean? We mean with a basic processing unit, like a microcontroller, a processor. Can we calculate it or not? Okay. Now one thing we're going to introduce is something that we call a twiddle factor, e to negative j 2 pi divided by n is referred to as Wn and referred to as a twiddle factor. And therefore, to simplify the notation, we can write the discrete Fourier transform as x of k equal the summation from n equals 0 to n minus 1 x of n multiplied by w sub n to the power of k multiplied by n. And we can write the inverse discrete Fourier transform as x of n equal to the summation from k equals 0 to n minus 1, 1 over n, x of k multiplied by w sub n to the power of negative k multiplied by n. Okay. So looking at this discrete Fourier transform, we have a signal in the time domain that is going to be of finite length. And we're going to calculate the spectrum for, or the discrete Fourier transform. So this is K, 0, 1, 2. This is N, 0, 1, 2, 3, etc. So as you can see, as you see here, both the time domain and the frequency domain are discrete. The frequency domain, if I want to calculate x of k when k is equal to a 0, is going to equal the summation from n equals 0 all the way to n minus 1 of the values of x of n multiplied by that exponential. And the same thing, if I want to calculate x of n from x of k 1 over n, the summation from k equals 0 to n minus 1 multiplied by that, multiplied by x of k multiplied by that exponential. So both in the time domain and the frequency domain, they are discrete and they are finite length. Together? Now what we're going to do next is we're going to relate the discrete Fourier transform, this one, to all the other transforms that we are familiar with. So let's start with the discrete Fourier transform and the discrete Fourier series comparison. And if you look at the discrete Fourier transform, it is simply one period of x delta of k. What does that mean? So if I have a signal x of n, and this signal looks, for instance, something like this. If I made this signal periodic, I'm going to get a signal that looks something like this. And if I take this periodic signal and make it aperiodic, I'm going to get one period of it. Okay. So since I have, if I look at the right side, I have a periodic signal. And therefore, if I want the spectrum of this signal, what do I have to use? It's discrete, and it is periodic. I'm going to use the discrete Fourier series. What is the discrete Fourier series going to give me? Going to give me x of k tilde. A spectrum that is periodic. So this is what we already know. Now we introduce the discrete Fourier transform. Now if I take the discrete Fourier transform of x of n, I'm going to get x of k. And if I make x of k periodic, then I'm going to get x tilde of k. And if I take x tilde of k and take one period, Together? So what is this again says? If you have a signal that is periodic, if you take the spectrum, the discrete Fourier series for it, you're going to get a spectrum that is periodic. If you come to this signal, you take one period of that signal, you take the discrete Fourier transform. The discrete Fourier transform is going to be one period of the discrete Fourier series of the periodic signal. So let's say the spectrum here looked something like this. This is K. What is the spectrum using the discrete Fourier transform going to look like? It's going to be one period of that. Is that clear, everybody? Okay, so basically what this says, as an example, the 10-point discrete Fourier transform of this signal here this is x of n is equivalent to one period of the discrete Fourier series of the following signal. This is n. 10-point discrete Fourier transform of this signal is equivalent to one period of a signal that has a period that is equal to a 10 that is repeated.
Then ellipses are like just dots.
Which one?
The dots.
This dot dot.
No, on the there is
This is this one.
no like the dots to yeah, on the ones on that line, but like between the 0 and
Yes,
10.
there are lots of dots, but because there are 10 of them, I just skipped, and then I put the index here. Does that make sense? So this is 0, this is 10. So in between them, they're all zeros. Okay. Let's look next at the relationship between the discrete Fourier transform and the discrete time Fourier transform. Now, hopefully, this will be the easiest one to understand because we're familiar with the discrete time Fourier transform. So here, if x of n is a finite length, and it has a length that is less than or equal to n, then the endpoint discrete Fourier transform of x of n is identical to the discrete time Fourier transform of x of n evaluated at n equispaced frequency points on the unit circle. So again, what basically we're saying is that x of k, which is the discrete Fourier transform, is going to equal to x of e to j omega, and sampled at omega equal to 2 pi k divided by n. Which we can also write as x of z, and evaluated when z is equal to j 2 pi k divided by n. Okay. So remember, when we calculate the discrete time Fourier transform, we're evaluating x of z along the unit circle, isn't it? So we evaluate it from 0 to 2 pi, or from negative pi to a pi along the unit circle. That will give us x of e to j omega, which is continuous. Remember that? Now what we're saying is, if you calculate the discrete Fourier transform of this sequence using the formula that we introduced, what you will be getting is samples of that response evaluated along the unit circle. This is k equals 0, k equal 1, k equal 2, all the way to k equal n over 2 at this point here, and k equal to n minus 1. And therefore, the frequency resolution is going to equal to a 2 pi divided by n. What is the frequency resolution? When I'm doing it continuously, I'm going from 0 to 2 pi. Then I'm taking these samples. What is the distance between each one and between two of these samples? 2 pi divided by n.
Yeah.
Make sense? And we'll see it more clearly in a second. Okay, one more thing. The frequency mapping between the discrete Fourier transform to discrete time Fourier transform is the following. When k is between 0 and n over 2, x of k corresponds to omega equal to 2 pi k divided by n. And when k is between n over 2 plus 1 and n minus 1, x of k corresponds to omega equal to negative 2 pi multiplied by n minus k divided by n. What does that mean? So when I am at this point corresponds to what omega? To omega equal to a 0. When I am at this point, k is equal to a 1, this corresponds to omega equal to 2 pi divided by n. Make sense? This k equal to a 1. Let me see there. K equal to a 1 corresponds to 2 pi multiplied by 1 divided by n. K equal to a 2 corresponds to omega equal to 2 pi multiplied by 2 divided by n. Now let's look at this here. What I just wrote is to this point, the mapping is correct all the way to this point here. After this point, the index for this point is n over 2 plus 1. From n over 2 plus 1 all the way to n minus 1, x of k corresponds to omega equal to negative 2 pi multiplied by n minus k over n. What does that mean? If I am at this point here, can you tell which one I'm highlighting?
Yeah.
Okay. K is equal to n minus 1. If I plug in k, I'm going to get n minus n plus 1 over n. What is that going to correspond to? Negative 2 pi divided by n. N minus k is n minus 1. So it's going to be minus n plus 1. N with n going to cancel. It's going to be 1 over n multiplied by negative 2 pi k.
Yeah.
Make sense? So this corresponds to 2 pi over n. This corresponds to negative 2 pi over n. There's symmetry along the y-axis. Okay. Okay. So therefore, if we are given n-point discrete time Fourier transform, or giving n discrete time Fourier transform samples, which means the discrete Fourier transform for k equals 0 all the way to n minus 1, we can uniquely determine x of n using the inverse discrete Fourier transform. And in one condition, which is provided that the length of x of n is less than or equal to n. And we'll see what this means in a second. Okay. Okay. So let's look here at the impact of the value of n. So we've been talking about n throughout the discrete Fourier transform. So what is the impact of this n that we choose when we calculate the discrete Fourier transform on the appearance of the discrete Fourier transform? So we're going to look at assuming that L, which is the length of the sequence, is less than or equal to n. What is the effect? What effect does the choice of n have on the discrete Fourier transform of x of n? So what does this question mean? So if I have a sequence that looks like this: 0, 1, 2, and 3. What is L for this sequence? 4. So I tell you, calculate the discrete Fourier transform for this. Somebody comes and say, okay, I'm going to calculate the discrete Fourier transform. I'm going to choose n equal to a 4. Somebody else is going to come and say, oh, I'm going to choose n equal to a 16. Somebody is going to choose n equal to 256. What is the impact choosing n will have on the appearance of the discrete Fourier transform?
The bigger the number, the more crowded it'll get.
Excellent. Yes. I mean, we can see it from here. The bigger the n that we choose, the more samples we are taking here, and therefore the better resolution we have of our discrete Fourier transform. Make sense? So, to answer this question, as long as L is less than or equal to n, any n that you take, any point DFT, will have complete information about x of n. About x of n. However, increasing n will increase the number of frequency samples of x of e to j omega. And this means we're going to have higher resolution in the frequency domain. Good? Now this process of choosing n that is greater than L is called zero padding. So the zero padding is the process of increasing n without changing the length of the sequence. What does that mean? So let's look at two cases. So let's say I have a sequence that has a length of 4. 0, 1, 2, and 3. And I have another sequence that has a length of 16. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is x1 of n. This is x2 of n. What is the difference between this signal and this signal? This signal padded with zeros. I padded 12 zeros to this signal. Now if I come and I calculate the discrete Fourier transform, the discrete Fourier transform is equal to, I'm going to choose n to calculate the discrete Fourier transform, n equal to a16. So to calculate x of k, I'm going to get the summation from n equals 0 to n minus 1 x of n e to negative j 2 pi k multiplied by n. Now whether I calculate x of k using this signal or x of k using this signal, I'm going to get the same results. I'm going to have values from 0 to 4, and then all the entries are going to be 0. And the same thing, values from 0 to 4, all the others are going to be equal to a 0. And therefore, both of them are going to give me the same results. Does that make sense? So therefore, if I'm trying to plot the spectrum of a signal in MATLAB, I can come to the signal. If I look at it and I don't like the resolution, I can pad it with a 0. Or I can just increase the value of n that I'm calculating the discrete Fourier transform with. Good? And again, we'll make this hopefully more clear as we go. But if you're working on the project, there's a command that's called centered FFT. Anybody use that?
I saw it, but I remember it from principles of engineering analysis.
Yeah. So the centered MATLAB, and soon we're going to be using MATLAB, but MATLAB has a command that is called FFT. What does FFT do? It's discrete Fourier transform. And if you look at the summation, it's slightly different than our definition. What's the difference? It starts at 1. And why does it start at 1? Because MATLAB.
Special.
Yeah, so everything just shifted by 1. But it is basically the formula that we just put here. Make sense? However, if I come to any signal and just say plot FFT of a signal, I'm going to get something that I'm not going to understand. So all what we're doing in this part is that when you go to MATLAB and do the FFT, you're going to put it in a form that makes sense. Okay. So let's do an example on the calculation of the DFT. So let's say that we have a sequence that looks something like this. Zero, 1, 2, 3, and 4. And this is 1. And this is x of n. And we're going to calculate the discrete time Fourier transform. And we're going to calculate the discrete Fourier transform. And we're going to calculate the discrete Fourier transform for different values of n. This is for n equal to a 5, for n equal to a 10, and that's it. Okay, so how do we calculate the discrete time Fourier transform? Remember, this is similar to calculating the x of z. This is going to be the summation from n equals 0 to a 4, x of n, which is a 1, e to negative j omega multiplied by n. And this is going to equal to 1 minus e to negative j omega to a 5 divided by 1 minus e to negative j omega. And here we're going to use the relationship, the geometric series that says the summation from 0 to n a to k is equal 1 minus a to n plus 1 divided by 1 minus a. Good? Okay, what do we do next? Every time we have an exponential to a power, what is it we like to do? We like to take half that exponential off. So we're going to take negative j 5 over 2 omega. I'm going to get e to j 5 over 2 omega minus e to negative j 5 over 2 omega. And we can do the same thing with the denominator. Omega over 2 multiplied by e to positive j omega over 2 minus e to negative j omega over 2. Okay. We can cancel this with this, and what's going to be left, this is 2.5 omega, and in the denominator is half omega. We're going to have e to negative j 2 omega, and then this is a sine of 5 over 2 omega divided by sine of omega over 2. Together?
Would it be
Mm-hmm.
negative j5 omega?
This is 2.5. 5 over 2, 2.5. This is 0.5.
Yeah, that's good.
Okay. So therefore, this is x of e to j omega. Now this is a complex quantity. So we can take the magnitude, we can take the phase. So let's take the magnitude of this. What is the magnitude of x of e to j omega? What is the magnitude of this exponential? Is equal to a 1. So this is going to just equal to the magnitude of 5 over 2 omega divided by sine of omega over 2. What is this going to look like? When omega is 0, what is this going to equal to? No. 5 over 2 over 1/2, which is 5. It's going to be 0 over 0. L'Hopital's rule, take the derivative of the numerator, the derivative of the denominator. And then this is going to look something like this. And this is when this will have a 0. This is going to equal to a 2 pi divided by 5. This is going to be 4 pi divided by 5. This is pi. This is 6 pi divided by 5. And this one is 8 pi divided by 5. And if I continue, this is going to equal to a 2 pi.
Quick question.
Ask me.
So for the equations that you have, you cancel out the e terms
Uh-huh.
in the fraction. Wouldn't the remaining number be a 5, not a 2?
No, because, I mean, it looks, I did not count, this is equal e to negative j, 2.5 omega, divided by e to negative j, 0.5 omega. I did not cancel, I subtracted them from each other. 2.5 minus 0.5 is negative 2. Make sense? Is that clear? Make sense? And please, if anybody if I write something like this not clear or you're not convinced, just ask. Don't let it bother you. Okay. We'll stop here. We plotted the discrete time Fourier transform. This repeats every 2 pi. And in the next class, we'll plot the discrete Fourier transform. And we'll compare it to the discrete time Fourier transform. Now, one thing I want to mention. I mean, this topic is very interesting. And if you understand it now, you will understand it for life. And we're going to try to cover every aspect that might create a confusion. Make sense?
Yeah.
So please pay attention, make sure you understand it, and hopefully if you do, you're going to always go back to your notes if you ever forget it, and